everybody. This is Paul Taubman with 9.Connects. Thank you very much for joining us here today. We have a lot to cover, so I'm going to get right into it here. This is the webinar in regards to making footprints. It's kind of a follow-up webinar that we did last month to symbol creation. And as usual, we have more information than we can possibly fit in 1 hour, but we're going to make every effort to do so. So who are we here at 9.Connects? Actually, interestingly enough, we get calls all the time asking us to sell them an Altium license, and once upon a time we were an Altium VAR. However, over time, Altium has pulled that back in, and as a result, we have moved on to other services. But we are a group of seasoned engineers and layout designers who really have come together to provide our services, and you can see a list over here, and we have examples of companies for each one of these lists who have actually used our services in one way or another that you see up here. More importantly, what are we here for? Well, I kind of look at 9.Connect as being the engineer's engineer, and we're really there to help fill in the gaps where there is a lack of skill or knowledge. Because the fact of the matter is, when it comes to PCB design, most of us have never really been formally trained on it. We went through school, we did a lot of theory, especially if you went through electrical engineering. You got thrown into the industry, you started a job, and next thing you know, you got to put out a printed circuit board, which is very much actually a manufacturing process. So when we have to get in there and do things that we're not familiar with, a lot of times we just don't have the time to research it because the project's got to keep moving forward. We just don't have time to take seminar-length classes, which take several months. We certainly don't always have the engineers who've always been there and done that, especially if it's kind of a startup and you're fresh and new to the industry. And many times, too, it's just a budget issue where you can't bring in a full-time designer or engineer. So here at 9.Connects, we are a PCB-centric service organization that can help you very specifically with your PCB design. We can help you with the design and the consulting of it. We can help you in library methodology. The key thing is simply ask us, because we are there to help you out. And that's exactly why we do these webinars, is to impart our knowledge onto you so that you can all be better PCB designers. All right, so with that being said, I'm going to escape out here and get to the good stuff. So you can see on my screen right now, we're looking at Altium Designer 16.0. And Altium added a new library in Altium Designer 15. And I wanted to bring this to your attention here because maybe you haven't had time to play with it. It's not a critical library, but it's a very useful library. And what they call it is the Pad Via library. And if you ever want to take a look at it, go ahead and go into File, New. You go into Library, and you'll see this thing that is called Pad Via library. And when you bring it up, you will see probably the editor. You probably will not see the panel here. If you want to bring up the panel, you can click at the bottom right corner where my cursor is located, and that is the Pad Via library. More than likely, when you bring it up, it's going to be blank. So what do we do with this thing? Well, the idea here is to be able to store both pads and vias that you have created so that you can reuse them. Pads obviously are going to be used for the PCB library. Vias are primarily used in routing on the PCB layout itself. But you can store both of those over here, and I've created quite a few examples as I've been practicing up to this webinar. So what do we do with it? Well, if I want to create a new pad or via, I just simply right-click in the area here on the Pad Via library that's empty, and I can add either a pad or I can add a via. So I'm going to just throw in an example of a pad. So when we do this, we get basically a new blank line. The editor clears itself out. And you're going to see this funny cryptic little name that comes up. Well, this name actually is following an IPC convention, and Altium can actually put that name together for you so you don't have to try to follow the convention itself. But in addition to that, as you move along, it's going to change it, which is really neat. So for example, if I want to have, and this is set up currently as a through hole, but let's say I want a surface mount pad for this. I can click on the SMT button. You'll notice this immediately has changed. Some of this stuff has been blanked out because it has nothing to do with surface mount. And then over here on the bottom, I can simply change this thing up so that it's round, rectangular. I can change the name over here, make this 50. If I leave this as 60, you'll notice that as I'm going along, the name is changing over here. If I want to see all of this in metric, I can simply change the display units over here from imperial to metric, and I can see it this way. Unfortunately, the Q key, which we tend to use for both the PCB editor and the PCB, don't allow it to flip automatically. As for the naming convention itself, it is done in metric. And if you're interested in knowing what this represents or stands for, there is a document out there. I'm going to bring up my web browser here so I can show it to you. So if you actually search for the IPC 7251 and you do a Google search on it, you will actually bring this up. This is one of the first things that comes up. And it actually comes from Boston University. So one of their departments over there looks like they, I don't think this is the original one. This is not usually in the format of IPC, but it looks like someone summarized it. And it talks about all of the different letters and characters that you're dealing with. As a side note, when it comes to things like the decimals and how do you do the nomenclature over here, they give a little bit of an example of it. So every number goes 2 places to the right, as many as needed to the left of the decimal. So they give you these examples. But it is all in metric. So that's one of the things that you have to just kind of recognize with this. If you don't like the naming convention over here, you can put in whatever you want. And of course, later on, if you regret doing that and you want Altium to restore it, you just hit the R key, and then Altium will give you, again, the IPC nomenclature for it. I also highly recommend some type of description. I've been playing with this a little bit over here because a lot of people aren't going to know what this means, and if they don't know what it means, they're going to try to avoid it. So the description certainly helps with this, and that's what I was trying to do. And of course, you want to organize it in such a way that if you were to click on description, it will sort accordingly. So that's what this is doing for you. If you right-click over here, you can add a V in here. It's going to look very similar. Obviously, it's going to have less features than what a pad does. Because a component pad, we have a few more features we got to deal with when we're making a footprint. So that's what this PV lib is all about, if you're ever curious about it. And by the way, once you set this up, there is a panel in both the PCB library and in the PCB that will show you these things, so you can just simply click on them. Or in fact, you just simply right-click on them, as I'll demonstrate today, and you can make use of them. Now, one thing you do have to do with this library is you do have to kind of install it like any other library that we have in order for your libraries and the PCB to see it. And in order to do that, you've got to click into the library. So here's the libraries panel. Again, for those people who are new to Altium, the libraries panel is strictly a placement panel, and it's where you can install your libraries. It has no bearing on any of the library editors themselves. You really can't take anything from here and add anything to any of these type of libraries. But you can do an install, and you do need to do that. So you go into libraries, make sure you're on the install tab. From there, you go into install, and you install from the file. And by the way, I'm not sure why it's not necessarily showing this PV lib as one of the installed libraries, but I do know it has been installed because it's visible when I go actually over to my PCB library itself. So in the PCB library, which I've clicked on, so this is the PCB library. Let me bring up the main panel here. In the PCB library, we've got a couple of regions within our panel that are good to note. Obviously, we have our components. This is the way we would see our components. We have our different component primitives, and sometimes I forget about this, that we can always use this as a select. A lot of times I do that graphically through Altium, but it's a lot easier just to do it here if you know what you're looking for. And at the bottom, if you don't see it, sometimes it comes up looking like this, but there's a chevron at the very bottom. If you click on that chevron at the very bottom right corner of it, it will bring up a magnifying glass, so you can move it around by clicking on your cursor. If you pull in the corners here, it will actually zoom it in. If you pull on the cursors, it'll zoom out. And of course, if you're doing any actions within the main editing screen, this will automatically update as well. If you are doing any type of searching here, just keep in mind the top here in terms of select, zoom, and clear existing. So when I click on something, you'll see that it selected it. It is masking everything else out. It is also zooming me in accordingly, and it's also clearing anything else that I had selected before. Even if you don't use this in the PCB library editor, you'll see a very similar thing in the PCB panel in the PCB editor. So it is definitely something very good to note. All right. If you ever need to clear up, by the way, and if you get into some type of filter here and you forget, there's two places where you can easily clear out the filter. You can click on the clear key up here, and if you've moved on to another panel, you can always hit the clear key down here at the bottom right corner as well. And I believe there's a shortcut key, but it eludes me at the moment here. So there's different ways to at least navigate around the PCB library. And of course, for the PCB library, this is a matter of doing a file, new, at library, and you do a PCB library. When it comes up and you don't see your panels that you need, make sure you go to the bottom right corner, click on PCB, and bring up the PCB library. One of the other panels I'm going to show you here, because since I showed you about the PAD VIA library, is the panel for the VIA PAD library, and I'm going to bring that up here right now. So there's three regions to this VIA PAD library, actually four if you want to include a drop down here for the different libraries you might have. What you see over here for this library are all the different pads and vias that I've already created in this library. And if I click on them over here, they will not update. However, if I want to make them local, I can simply drag on them and bring them down. So if I want to make this here, I can drag it down. And once I've brought it down over here, I can now see it. By the way, I can place on any of them here. So if I want to place here, I'm saying, look, I don't need to bring it into my pad via library here. I just simply want to place it. I can certainly do so, and there it is. It's just that when it's in this local pad and via library, which is basically the library, the PCB library itself, it allows me a preview of it, whereas I don't see a preview of it when I'm just looking at the library. So that's just a little note to make. But now I've got these pads available to me, and I can use them as I see fit. Can I use vias in here? I certainly can. In the PCB library, I can use pretty much any type of copper primitive you see on the PCB with the exception of a copper pour. I'll talk a little bit about that a little bit later on. But even copper pours, when they're copied in from a PCB into your library, can be converted into copper regions. The big difference is, and the reason why you want to use pads in your library is because they have something called the designator. So it's really important to have this designator because this designator is how Altium relates your design pads to your symbol pins. And if it doesn't have a designator, there's ways of adding a designator to it, but it makes it a little more complicated. So the easiest thing to do is to actually use the pad primitives in Altium in order to make your parts. Now the part that I'm going to make today is one that kind of continues from the last seminar, and it was the LN741. Now you may also look at this one, for example, and say, man, he's going to do some old technology over here. But in talking to various individuals about libraries, one of the things that's become very apparent to them, you'll never get 100% away from through-hole, first and foremost, because good connectors can take advantage of that through-hole, and it actually provides additional strength to the connector, especially if there is a lot of pressure being exerted due to the cable weight or just by the vibrations of things that are going on within the board and the system itself. So at one point or another, you are going to have to come across through-hole, and there is a little bit of thought that has to go on with that. Surface mount is not as, I'd say, as difficult as the through-hole, believe it or not, and Altium does have good wizards for it. As I mentioned during the webinar preview in the emails that you received, I'm not going to go through these. We do have videos up for them, but they are extremely useful, and I highly recommend it if you are just trying to get something very quick and easy together for surface mount. But when it comes to through-hole, it does require a little bit of thought, and we're going to draw this out step by step. One other thing I'm going to mention to you that's really, really important before we continue on, and we talked about this a little bit during the symbol presentation last time, and this is setting up your files and setting up your primitives accordingly. And one of the most important things that you want to set up when you're dealing with your PCB is your mechanical layers. So if I hit the L key, which gives us our view configuration, you can already see that the mechanical layers I want to use are always set up. Why is this important? Because if you're not consistent with this and you start placing down parts with different mechanical layers, in the end, it becomes very difficult for you to clean up your PCBs when you're getting them ready for documentation, especially for what is called the assembly files. All right, and by having this stuff set up properly and everybody following it, basically your documentation writes itself, because as you've got these parts coming down in your PCB, as long as everything's been done and done on the right layers, your documentation's already going to be there. And so it's really important that this happens. Now, unfortunately, if you try to save off this configuration and then open another PCB library and then try to bring in this configuration, it will bring in everything except for the mechanical layers. So it's a little bit of a flaw in the tool here, but there is a workaround for it, and that's what I want to show you here. So if you know that people are going to make footprints on their own and you want them to adhere to this, then what you can do is you can always create a file in Altium, and this is true for any file. You can always create a file. You can do a file new, and open whatever file that you want, and you can set it up the way you want it, and then you can make that kind of your new file, or what they call new file document default. And what I did over here, for example, is if I go into DXP Preferences, okay, and under System, and we click on New Document Defaults here, Altium says, look, I have all these files by default. When you open it up, it always comes up with a blank screen. So for example, for a PCB dock, it always comes up with a 4x6 inch board already by default. But if I want something different, or if I already want some of the layers already set up, I can certainly do that. And once I've taken that new file, set it up the way I want it to, and then save it, I just have to tell Altium where to go find it. And every time I do a file new of that file thereafter, it's going to bring up the one that I already set up. All right. Now, notice just one little caveat with this is that you can set up documents both in the context of doing it in a project, but in my case over here, I actually did them as a free doc. So for my PCB library, every time I do a file new library PCB, it's going to actually use this template. And so just to demonstrate this here, I'm going to bring up my projects here, and I'm going to go into File, New, and I'm going to do a library, and I'm going to click on PCB Library. So a new PCB library is going to come up here, and if I hit my L key, you'll now notice that all my mechanical information is here because that's a part of my document default. So if you are going to have people work on libraries separately, and that's a very common practice, a lot of people will say, build these footprints for me and then I'll get them into a central library. That's fine and dandy. Just make sure everybody's working on the same mechanical layer. And so there it is. If I also wanted to set up other things like the different grids, I could. So I got to be perfectly honest with you, I'm changing grids all the time. So getting kind of bent out of shape about grids on a new document default is kind of a waste of time. Let me jump over here. I'm going to close this one. We don't need it at this point. So I'm going to go over here to my webinar PCB, one that I've already kind of started, and you can see that we've got this example, but I'm going to start a new part and go through the motions of it. So I'm going to do a new blank part, and just so that I can find it over here, I'm going to call this A-LM 741. The A is just to get us to the top of the order. And of course, I can give it a description, which I'd recommend. There's one little thing, and I have to investigate this a little bit more. Normally, this type over here was provided to the symbol, and these types over here show the relationship of the symbol to the footprint. 99% of the time that the relationship is going to be type standard, meaning that the relationship between the symbol and the footprint is a one-to-one, where the pin represents the pad. But if you have situations like you're making inductors where you have to do a net tie, or there are things that need to be in a bill of materials, or things that should not be in a bill of materials because they're embedded into the board, you can make those exceptions here. Though, again, normally this was always handled on the symbol side, so I'm not necessarily sure why Altium put this over here. It's something I'll have to take a look into. But nevertheless, for now, I'm going to leave it as type standard, and here's my name, and I'm going to press OK. So I've got my new, here it is. I just got my new component ready to go. So let's take a look very briefly here at our specification. So the specification over here is showing us a couple of things. The key thing that I need to recognize is that I've got 8 holes here, and that the center to center, from the center of the hole to the center of the part, is 100 mils. Okay, it's a pretty big part. And then more importantly, what I've got to worry about is the pin shaft itself. Basically, if it's square, it's going to be the diagonal of it, or if it's round, it's going to be the diameter of it. And you can see that it can be as small as 16 mils and as large as 21 mils. Now, why do I care? Because in the end, I've got to come up with a hole that works, and I got to come up with an annular ring that works. And the IPC actually has some rules to assist with this to ensure that it will indeed work. So give me a minute here, because I'm going to definitely bring up my my PowerPoint presentation here again, and I show you a few slides on how we figure out how we do the holes in the annular ring. So from here, and then of course we're on this one. So again, don't hesitate to ask us here. We're here to help you. All right. Oh, and I should mention this too. If you have any questions during this webinar, feel free to write them down in the questions panel. And if I have time today, I'll certainly try to get to them. If not, we will provide a Q&A document afterwards upon request. All right. This is what I wanted to get to here. All right. For the through holes, we have to deal with the fact that there's tolerances, and these tolerances are beyond our control. So for example, if we look at this, and I like this picture because it kind of shows the idea of a peg going into a round hole over here. And the question is, what does it take to ensure that this peg would always go through this hole? So think of this green area, or this green shape, as being the board, and this red cylinder as being the pin, the through hole pin here, and or the lead. And the idea behind this is that we have to realize that there's something called a maximum material condition and a least material condition. If you're interested in this, the IPC goes into a lot of details. They also provide something called a CID, and they talk much about this. So if you're interested, do contact them about this, because it's really an important thing, especially if you're going to be doing through holes, to understand it. And when you're talking about maximum material condition, what you're talking about is how wide is this pin going to be. And on a board over here, the more material you have, how small the hole is going to be in terms of its diameter. And you can have 2 corner cases. One corner case is in which you have the pin at its largest, okay, at its largest diameter, and the maximum material for the board means that the hole is at its smallest diameter. And in some cases, if you don't do this right, the pin isn't going to go through the board even though it worked before. Okay? It's because, again, there's just two different tolerances that are out of your control, one from the manufacturer and one from the fabricator. On the opposite end, you also have a least material condition, which means that this pin is at its smallest, or the diameter is at its smallest. And in a least material condition on the board, the hole is at its largest. And if this is bouncing around a bit and you put it through wave solder, it may be too small and the solder just can't stick to it because gravity's kind of pulling it away. All right, so there has to be a happy balance over here to ensure that this always works every single time. Now, to complicate things just a little bit more, and it'll make sense here in a minute, in order to understand IPC's, I don't call them regulations, but their standards, they always have classes. And as a matter of fact, it'd probably be surprising if your fabricator isn't asking you for a class. And the reason why these classes exist, it determines the level of reliability. How much tolerance do we need to do? Because you can make a board that electrically works, in theory electrically works, but may pass A and B, but not Class C, depending on what the requirements were from the IPC. Okay? And they break it down based off of the type of electronics. And trust me, there is a lot of gray area between each one of these classes. So, for example, let's take the most, I'd say the most blatant examples of each of these classes. So for Class A general electronics, Happy Meal toy, I've made references many times, but they do, right? They've had Happy Meal toys in the past that had some electronics in it. It's a general electronics. If it breaks 10 minutes after the child gets it, all right, there may be a few tears in their eyes, but it's not going to be the end of the world by any stretch of the imagination. All right, now we get on to Class B, dedicated services, where if these systems do go down, and it's not just ATMs, it can also be your cell phone as well, that's going to cause a lot of problems. It's going to inconvenience you tremendously. There could be some money on the line if there's financial transactions going on, but it becomes a major inconvenience, and the more downtime there is, the more problematic it becomes. And lastly, we have Class C, which is high reliability. And this is in the situation of like avionics equipment or in your vehicles, especially if they're doing drive-by-wire, and even life support systems. If these systems go down while they're in use, lives are either going to be at risk or they're going to just be lost. And so that's why they have these different classes. And obviously, with these different classes, your yields are going to be lower. There's going to be tighter tolerances, and they're obviously going to cost more. So there's a trade-off between each one of these classes. And of course, there's always that fuzzy area too, like cell phones. For some people, as far as they're concerned, it's probably just a Class A because they don't use it for anything critical. But for someone who's running their business off a cell phone, it could definitely be a Class B type of device. So the class should be determined by your fabricator. Definitely have that conversation with your fabricator. But the key point I bring this up, you're saying, what does this have to do with footprints? What it has to do with footprints is that IPC bases all of its requirements on these classes. So if we go to our next slide over here, if we look at material condition, which we talked about 2 slides ago, and we talk about class, we get our whole requirements. So if you go through IPC standards, if they do have to break them down, you will see that. You'll see 3 requirements based on A, B, and C. And so what I did here was I decided to do it for Class C for through holes. And what they said was like, we have to take the corner cases into consideration. So for the least material condition, no hole greater than 24 mils over the minimal lead diameter. So in our example here, we have 16 mils. They're saying no more than 24. So our maximum hole size needs to be 40 mils. Okay? If we go anything larger, this pin may be floating around. When we go through the wave solder, it may not stick because there's just too much air gap between the pin and the hole. And on the contrary side, obviously the maximum material condition, we got to make sure that that pin will even go through the hole. So you take 6 mils over the maximum lead. So it was 21 mils, we add another 6 to it, and then we get 7 mils. So this is the range that we get to work in. So it's really a matter of picking something. Now, in my case over here, I decided to go with 30. First and foremost, I do like overall round numbers. But more importantly, I really want to put it more in the center here to give myself a little more headroom. So the no less range, right? The minimum here is 6, so now I have actually 9, and that makes me feel a little bit better. One other thing I'll mention to you as well, a lot of people, and EDA tools allow you to do this. You can put in odd numbers if you want, but the smaller the drill, the less likely that the fabricator is actually going to have that kind of drill in terms of an odd drill. Usually they have even numbered drills, so it may behoove you to just go to an even number. Plus, I also find that a lot of things you do, especially in Altium, are symmetrical, and it's a lot easier to do things in a symmetrical fashion with an even number than it is with an odd number. So just bear that in mind as well. So it looks like our hole based off of these requirements will be 30 mils. All right, let's jump on over here to the annular ring. The annular ring is basically the copper that goes around the holes. It's on each layer. There's been a lot of debate on Altium's forums as to whether or not you want them on the subsequent layers, but they do provide an additional strength to the hole itself. Okay, and as a matter of fact, the IPC will call out for larger annular rings if that component that you have is of a certain weight, because you got to remember that annular ring is supporting this barrel and it's supporting the copper, and if there's not enough copper over here, it could actually get ripped out by vibration or other things because the part is so heavy. So the annular ring is definitely an important aspect of it. All right. So it provides strength, especially for heavier components. So definitely take a look at your data sheets and look at the IPC standards for recommendations on that. It does provide some reinforcement to the barrel, especially something this large. And it also provides a target for the drill. Now, what do I mean by that? Well, one of the biggest problems you have, and again, this deals with the classes, is that in a ideal world, it would be like this, okay? But in the real world, there is going to be some travel by the drill. The drill is going to go in at an angle, okay? And it's not always a perfect thing. And of course, there's what's called registration as well. And I'll talk about registration here on part C. So here's the ideal one where my cursor is located of these four. There is this situation called a breakout, and in Class A, and I think even in Class B, you can get away with breakout. In Class C, this is not acceptable. But also, if the drill wanders too close over to the trace over here, there's a certain percentage you can get away with Class A and Class B that you can't get away with Class C. So what they're recommending, at least in this example, is that you teardrop it, which is something you can do in Altium Designer on the PCB side. But for our purposes right now, the question is, we have a 30 mil hole. What would work best for our annular ring? So the IPC has a very general formula. And I call it a general formula because, again, this is a conversation you really want to have with your fabricator, but I'll just give you some numbers to kind of to think about. So the first one is basically the max hole drill size for your finished hole and for your inner layers. So we've got 30 mils. Usually they plate for 1 mil, and so I'm going to give this a value of 29. I could leave it at 30, right? But I'm just going to try to just give you some ideas of those things you need to kind of contemplate. For 2B, we have a minimal annular ring on either side of the hole. So it's a 2, so I got to multiply it. So if I want to have at least 5 mils on either side of the hole over here, I need to have an additional 10 mils diameter added to my annular ring. If there's etch back, the max allowed. So the etch back is those situations where this here is being called out, but you have to remember that copper is actually the whole fabrication process is a negative process, so we're removing copper. And depending on the way they do the process, it could etch this back a little bit more than what I expected to. So I have to make a little bit of an allowance for that. And then, and lastly, over here for the fabrication allowance on capacity, capability, and board size. So on larger boards, especially ones that are really got a lot of layers to them, and if they're really large, each one of the layers may actually move a little bit. There can be a little bit of a delta. They can slide to the X or slide to the Y. You got to remember that the dielectric, before it becomes a core, when it's heated up, it is actually a very mushy substance. We're talking about a woven glass which has flex to it, and we're talking about a resin which is kind of it's got a very thick viscosity, but it is still a semi-liquid at that point in time, and things can float over. So what they may say is they said, look, we need to account for this. We need to add an extra 5 mils or so many mils onto this annular ring to ensure that if our drill bit does travel a bit, it won't be a loss. Okay. So when we take all these and we add them together, we get 45. And again, if I can go something larger than 45, all the better. Okay. Now, obviously, there's real estate issues we got to deal with, but something this large, 50 mils, is going to work just fine. So therefore, in very quick summary, what we've got now is we have our hole and we have our annular ring, and we can now run with this. So let me push this off over here and move this over, and let's start doing some drawing over here. So let's get a hole going. So I'm going to do, just to demonstrate the new PCB library over here, I'm going to actually bring in our 50 mil our component over here. So I've already got it set up, and I'm going to right-click, and I'm going to place it. And if I hit the tab key over here, you'll notice one thing is generally I can't change anything here unless I actually unlink it. But for now, everything is set up the way I want it to be set up. So I've got my 30 mil hole size, and I've also got my annular ring at 50/50 here, because I could make it a little bit longer or oblong if I wanted to. It is set for multi-layer, which indicates to Altium this is a through hole. I've also, I really didn't need to do this in the paste mass expansion, but I just want to talk about it for a moment, because you really don't use paste on a through hole here. But for paste mass, usually I do a -1 mil, because I don't need to have the paste go all the way up to the very edge of the copper. When paste gets flowed, it will actually spread out. This works much more, obviously this is more apropos for a surface mount, but I had put it in there and I realized afterwards it really doesn't make sense, because when you wave solder, it's just the solder is just hitting, you don't really do a paste on it. And then in addition to it, the solder mask expansion I do because I want to make sure that there's just no solder mask whatsoever on those things that could possibly be soldered. And if I don't want it to creep onto the pad itself. So that's why I usually give an expansion to it. All right, so I'm going to press this down. Now, I want to place this 100 mils over, and I could count this over. And when I say over, I'm talking from the center point here. But I'm going to do a little trick here to make it very easy. I'm going to hit the G key, and I'm going to change over to 100 mils. So what's really cool about the grid and Altium, I can change it on the fly anytime I want, whether I'm in a command like a place command that I'm in now, or if I'm just kind of zooming about. So I can just drop this down. And I could place these other ones over here, but I want to show you a little bit about a little trick with the copy and paste, because if we go back over to our specification, all right, we have to put this at a 45-degree angle. And I could figure that out the hard way, but why do so when I can use my copy and paste? At first, a lot of people who are new to Altium, they find the copy and paste on the PCB side a bit of a hassle, because when you do a Control-C or you do edit copy, Altium wants a point of reference, and people don't remember that, because normally in every other tool you ever work in, Control-C grabs it and you're done with it. But in the PCB layout and in the PCB library, you do have to give it a point of reference. So I'm going to do that right here, and it becomes very powerful because, again, of the concept of symmetry. And because I have this over here, I can now paste these each in at a different angle. Rather than trying to figure it out, I can just have it go along in 45. Now, by default, if I select something, I'll drop it down over here. Let me do this. I'll place it. So I'm going to place this just for a moment. When it's on my cursor here, I can hit my, not that you're really going to see it because this is symmetrical, but if I hit my space bar, okay, it will actually go around. Now, you'll notice that it's going at 45 because I set it up at 45, but if I've got it on my cursor and I'm moving it around, I can hit my space bar and I can do the rotation. And the rotation by default in Altium is set at 90 degrees. I can change that. So if I go into DXP Preferences, I go under PCB Editor, go under General, you'll see that there's a rotation step here. I've changed it to 45. Okay, so as a result of that, what I can do here is I can do I'll select this first pin, Control-C, I'll put it over here, and now I'm going to do a Control-V. There we go. There's my Control-V. I'm going to hit my space bar, and now I've got it dropped in, and I just have to do this a couple more times. Control-V, space bar drop, Control-V, space bar drop. All right, you can see where I'm going with this. Control-V, space bar drop, Control-V, space bar drop, and one more time. There it is. Now, if I accidentally placed one underneath here, I can quickly check. I can sweep over this, go into my PCB inspector panel, and I just make sure I actually have 8 objects. If I see 9, then I know that maybe I accidentally put a through hole on top of a through hole. So for many people, they'd be very happy with this, just that we have to change out the designators. Now, at first you might say, that's kind of a hassle. Now you got to double click into this over here. You got to click into the designator. I'm going to press 2, then I'm going to move my cursor down and press OK. But really, most of this can be done by hotkey. How is that? Well, I have to double click into to get into its properties. But notice that the designator is already the active tab or the active region. So really what I just need to do is I can hit the 3 key. And then more so, if you look at OK and cancel, these are actually associated with the OK being with the return or the enter key, and the cancel is actually with the escape key. So I can just hit 3 return and not do anything else in it. So if I double click into this, I can do 4 return. All right. So the biggest hassle I got to do here with my is what I have to do with this is just basically double click into it. So 6 return, 7 return, and we'll be done here in just a moment. So pretty quick and easy as for what we got out of it. And trust me, for the time I saved on trying to get this aligned properly at 45, that was a lot of time that was definitely saved on this. All right, so again, as I mentioned, for most people, they'd be pretty happy with this and they would move on. But we need to provide a little more information. What can we provide? Well, let's throw a few silks in there. I'm not always a huge fan of them, but for something this big, it's probably not going to be a big issue. So I'm going to do a full circle here. Actually, before I do that, I'm going to jump to my top overlay, so it is on there. And I'm going to do a place full circle. Now, again, I need to change my grid out. I'm going to hit my G key. I'm going to drop it down to 10. All right, and there it is. So you can see, and it allows me to repeat it. And there's my silk. Now, if I want to get a little bit fancy with it, let's take a look at our design here one more time, or our layout. There's a little bit of a tab on 8 here. I think that's so that you know where the orientation of the tab is going to be. So let's put that in. Usually it's on pin 1, but interesting enough, it's on pin 8 for this. And what I'm going to do with that is, rather than try to draw an outline on this, it's silk, and so I just need to indicate it somehow. So I'm going to draw a little box and just put it in a 45-degree angle. So I'm going to go into place, fill, and I'll draw my box over here. And now that that's done, I'm going to click and drag on it. Okay, so I'm left mouse clicking and holding, and then I hit my space bar, and I just put it over here. And I suppose if I spent some time, I could really get it all nice and lined up. But again, it's really just to indicate what the orientation is for this, and I'm a happy camper. Now, I want to get this information onto my assembly layer. So going back again, I want my documentation to make itself as I'm going along. Well, I want to copy what I just did on the silk down there, because I may as well use it. And the way I can do this very easily is there's a key called the Shift S, and that puts me into single layer mode. And by doing single layer mode, it's easy to select things that are just on that layer alone. So again, I'm going to select sweep over, so it's just doing a left mouse click, sweeping over everything, making sure it's fully enclosed within the box. And I'm just going to do another Control C. So you can see me doing a lot of this. I'm going to give it a reference point towards the middle. I'm going to jump down to mid layer 6. All right, so here's mid layer 6. If I do a Control V, it will paste it back onto the overlay, and I don't want that. So I need to go into Edit, Paste Special. All right, and I got to make sure it's going to paste on the current layer here. And it doesn't show it initially, but once I've got this drop down, there it is. As for the circles here, obviously they're through holes, so I'll have to draw those in. But again, I'm just going to take advantage of the copy and paste. So I'm going to go into place. Here's my full circle. I'll put this in over here. And from there, I'll do a Control C since it's already selected. All right, and I'll just Control V it and just do this very quickly. Again, doing Control V followed by the space bar, then clicking to lock it down, Control V, space bar, lock it down, and we'll do this again, and there it is. The only other thing I'd recommend that you put over here is the designator, and that can be done by going into Place, String, okay? Now notice it automatically came onto my cursor, but many cases it probably won't. It'll probably have something else like this on it. So how do I get to a dot designator? Well, in Altium, any of its special strings in the PCB library, in the PCB editor, start with a dot. And when you bring up the dot, it brings up all the special strings. And if you put these down and you switch it to what they say convert special strings, it will give you basically the value. And the designator is one of these in here. So you double click on it to bring in designator, you press OK, and there it is. So when this part is placed down on the PCB, the dot designator will be converted to the actual designator that was assigned to this part. Okay? And of course, the designator on the silk is automatically given to you, so you don't have to do that in the library over here. But if you want this designator on any other layer, then that's how you do it. Okay? So now I've got this set up. Let's do a Shift S so I can see all the layers again. I also want to put a 3D onto this thing. And the 3D is really not that hard to do. I went initially looking for one. I said, this is crazy. I can do this in Altium in very, very fast form here. And just to demonstrate to you, I'm going to do that right now. So I'm going to go into Place, and I'm going to do a 3D body. Okay? And actually, before I do that, let me bring up this for you so you can see it. All right? There's really only 3 things I got to make. I got to make the can itself, the rim of the can, and the leads. All right? And I've already done the numbers over here, so we can rip through these kind of quickly so you can see it. But what I did was do Place 3D body. I am going to do cylinders for all of them. That's what makes it very easy. I don't even have to worry about extruding it where I got to draw off points and stuff. And we'll just start doing these here in a very short order. So it wants the diameter. This one's 167.5. Its height is going to be 185. Okay, and its standoff height is going to be 80. The reason why it's going to be 80 let's bring this back up here so you can take a look at it, is that there's actually 40 mils at its maximum between what they call the seating plane and the bottom of the rim, and then the rim itself is another 40, so I want it to be 80 up in the air. Okay? So when I draw this here and I press OK, and the cool part is I just center it off and I'm done. All right. Actually, I'll draw the other ones, and you'll see that they'll quickly come into play once we go to 3D. So let's do 185 over here. Its height is going to be 40, and its standoff height is going to be 40 as well. Drop that in here. All right, and now I got to get the little legs in here. So it was 21. I could put for its maximum. I could put put an odd number in here, like 10.5, but I'm actually just going to make it the radius at 11, and so the diameter will become 22. For the height here, at this point, believe it or not, it's going to be minus 60. And pardon me, the height is 100. The standoff height is minus 60. The reason why is because these pins have to actually go through the holes themselves. And so even though the height is, I've got to compensate for the fact that I have 40 height that I'm starting at already above the plane of the PCB. All right, so I've got these here, and I'm going to just drop each one of those in. Click. All right. Okay, and one more to do, and that's it. And there they are. You can see how quick and easy we made this here. Obviously, I probably spent more time doing the calculations, which took me maybe about 20 minutes. And then once I had those, they kind of went into play very quickly. And if I hit the 3 key here, there it is. Okay, there, and that works perfectly well for what I need. All right, so if I want to shift it around, right mouse click. I'm actually just got to make sure my reference is okay here. There we go. And if you're interested in more of these things, a couple of months ago we did a webinar on this. Take a look. I go into a lot more detail about these things. Lastly, what I need is a courtyard. And the courtyard is really important because, you know, say for instance this was a high voltage amplifier. And maybe the specification says, look, you need to keep some space around here. Well, when I'm putting these things down on the board, sometimes the 3D doesn't call out the whole story. I may need some more space around this for whatever reason or not. And the courtyard still helps with that even to this day, even though we have all this cool 3D stuff. So I am going to draw a courtyard. And one of the things I find really easy to do is if I do the following, I'm going to do a place fill on the courtyard level. And the reason I do this first is because it gives me a little bit of a, and it's not perfect, but it'll work. This here, there we go. I don't want to get too persnickety about it, but the idea behind it is that I find it hard sometimes to draw lines, and it's easier just to put a box first, and then I can place the lines afterwards. So now I'm going to draw the lines in, and now I can just follow the edge of the box, which is a lot easier than trying to look at all the guides. And there we go, and I'll right click and I'm done. I can take the box at this point and I'll delete it, and now I've got my courtyard. And there's my part. Okay, so that's a part in general. Now, what I do want to talk about is something that happens quite often that I think is really important to remedy. It was done for a good reason, but I don't think people think it through because they don't always know the assembly and fabrication process. What if I wanted to put some type of heat sink from here down to my plane so I can get some thermal release done? Well, what do most people do with this? What they're going to do is they're going to go here and they're going to place a pad, okay? And I'm going to hit my tab key here, and I'm going to show you how to do a pad here. So I'm going to do multi-layer. Let's make this hole size 75, okay? And I'm going to make my annular ring 100. Okay, so it's going to make a pretty big via hole over here. I'm going to press OK. I'm going to put that thing right here, okay? I'm also going to delete my, I'm going to delete this particular silk here. So let's do a delete on that. And I'm also, so let's just leave it at that. And people say, yeah, there you go. I've got this really nice hole over here, and then it can take all this thermal, take the heat away from the part. The problem is here that this is a huge hole. And if you're going to try to put solder paste or something through it, or even if you try to put, it's going to go through a wave solder here, there's nothing to hold on to, where these have pins to hold on to, right? You have a pin going through a hole, so the solder holds on between the hole and the pin. Here I've got nothing, and if I put some type of solder paste around this thing, it's just going to melt and go straight, it's going to literally just act as a drain straight through, and you don't have any connectivity to it. So this would, in order for this to work, you somehow have to come up with a way to fill it. Now you can do a VN pad, but that's kind of expensive, and there's other ways to do this as well. Now the other thing people say is, well, what about tenting it? Well, you can tent it, which means that I put the solder mask on the bottom. but how strong is that solder mask going to be? Okay, and so you're trying to treat this like a paper cup, and you know, it probably won't work because you know, with the heat and the amount of pressure and things that are going on, if you put solder paste in there, who knows if that solder mask is going to hold up during that assembly process, because it's very, very hot, right? And if this is going through a wave solder thing, it's probably just not going to, I don't think it's going to hold up at all. So what's a better way of doing this? And by the way, if it's a conversation to have with your assemblers, because they may have a solution to this, but you definitely want to have that conversation before you throw this out to them, and then they're looking and saying, I can't use this hole that you've got. All right, so what's a better way of doing it? Well, we can use a surface mount pad. Okay, so I'm going to do this here. And just because we're a little bit pressed for time, I did a little bit of work ahead of time here, so I'm going to use a few of these. You may have noticed that I call some of these webinar here. So what I'm going to do is I'm going to place these down here very quickly. So I'm going to place down this pad here. Okay, and then I'm going to place down these smaller pads. Just right click and place. Okay, and I'm going to put, let's see, I'm going to do this here. Unfortunately, it's keeping these. Now, I do need to change. One thing to notice about this in the middle here, all these pads do need to be changed to another value. And I would recommend that they would actually be given pin 9, and that a separate pin altogether is given to it for pin 9. And the reason for that is that this would currently be associated with pin 1. So even though they're not attached to each other, Altium will say pin 1 is associated to this and all of these over here. Now, what I can also do, just show a very quick trick, I can right-click on this. We can do some find similar objects. And I can say, okay, I want you to find all the pads on the top layer, same, and I'll press OK. And it will run the, not doing it for the whole library, it will select those matched ones, and it will run the inspector. So, and I know it's been doing a little bit of this odd zoom out over here. I'm not sure why Altium's doing that right now. But notice that it now has all these pads selected. I'm now going to change these names over here to pin 9. All right. And when I press return, they'll be in there. I'm just going to do a VF, which is view fit me back in, and there we are. So I have those pads in there, but I also got to put some through holes here. So the idea here is to allow me to put some solder paste over here and then move off these through holes so that they're not, so that the solder doesn't go into them. And I'll show you something else I did to these too, but I'll wait until I put the, just wait a moment while I put these other ones down. So for this webinar, I'm going to do this. I'm going to place these. Okay, so let me hit my tab key here to change this to pin 9. Okay, and I'm just going to quickly place each one of these down here. Okay, so this one could be moved in a little bit. Now it's fine for now. It's acting a little persnickety, but that's fine. So I've got it in here now, but the idea is this. When I go over to my solder mask, and let's go over here to my top solder, and let me also turn off the mechanical, because the mechanical color here is the same. Turn these off here so you can see it. So what's happening over here, and again, these need to be turned off. I guess I didn't turn them off. The idea behind this is to turn these, and I have to unlink it. There we go. I'm going to force tenting on the top. So you'll see if I did this to all of these, the point here is that the only place was opened in the solder mask is right here, and then you'd actually have the rest of this disconnected, even though the copper's over here. If I go to the top layer, the copper is over here. These things are actually under a solder mask, and as a result, it can't creep over into the hole. And that will allow you to put a solder paste over here, which you're going to have to do anyways before. You're going to have to put the paste down. You're going to put your part through it. They're going to put it through wave solder. It's going to melt this, and you'll have a better shot at actually making thermal conductivity between the bottom of your can to this over here. So every time I see something like, and I'll show you another example, one that always worries me. Here's one that comes from Texas Instruments, and what they're saying here is that they want you to put through hole pads all throughout this. So be careful of this, because again, you'll put solder all over this area here, but how many of these are just going to basically become drains for that solder paste to wick through as you heat it up? So be very careful when they call out for things like this. Talk to your assembler and talk to your fabricator about those type of things, and see if you can arrange for another way to provide thermal conductivity to your planes without losing your solder paste in the process of doing that. Okay. Let's see. I have a few more minutes. There's our part over here, and I guess if I want to be a little more clean about this, let me do another find similar objects, and I want to find all of those that have the same, let's see, that have, here we go. I'll find all of them that have the same X and Y annular ring, and if I press OK, I should have all 4 of them. There they are, and what I want to do is I want to turn off the paste, or the tinted, mask tinting on the top. So I want to make that true, and there it is. So just a matter of finding it in here. And I could click into each one of those and do that as well. I didn't turn off for the bottom, that's why you see the bottom ring here. So there's our part, okay, and it's all good to go. And again, remember, I did turn off the mechanical layers. The last couple of minutes I have for you, I want to show you something that's really kind of off the cuff, so bear with me on this, but I think it's going to be kind of useful for you to see it. It came in late last night, and I said, you know, man, I don't know if I have time for it, but I wanted to show it to you because I thought it was really interesting. Probably the most insanely complicated footprint I've ever seen, so up to date. And it came in, it's from ST Micro, okay, and it's sent to us by a customer. And the customer is like, how do I draw this thing? So the bigger question is, how did I get this in here over as such? So I did contact these guys today. I was hoping to get a DXF DWG file. So that's one way to go about doing this. If you come up with an incredibly strange and unusual pattern here, yeah, the ST Micro here, I can bring it up, and you can see the pad. It's really, really intricate. And if I can get to it here quickly, you can see that the land patterns are all over the place. Plus, they have some things that are unique, and that's what I want to talk about as well. So if they can give you the DXF DWG file, then what you'd want to do is to simply import this in, okay? And they didn't give it to us, unfortunately. I'm asking them for it, and I think it'd be something useful for them, especially for any of their customers who have to build this really intricate land pattern for it. So there it is. But for the time being, what did I do? So actually what I did here is I took a picture of this, okay? I took a screenshot of it, and I brought it into Altium Designer. And you can do that. You can do screenshots and do a copy and paste and drop it in. So if I double click into this, let me hold down my shift key to double click into it. I do lock it down, but it's just a picture. And what I did from that point on was simply just draw these in. Now, to get down to this granularity, what I had to do for the grid was I had to go into View, Grids, all right, and then I set a snap grid, and I can make it extremely low, and I think I did it at 0.25. And from there, I just simply drew these things out the best that I can. Are they accurate? No. And by the way, be very careful about PDFs in general, because PDFs, it's one thing, it's one of the picture, but if they're doing any type of vectors in there, they can be off a little bit. I had experienced that when I did support with Altium many years ago. It was actually an MIT student who was trying to print these things off in a PDF and then do some type of PCB process in the lab that he had access to, and we were having problems with it because the PDFs didn't have the accuracy that he was looking for down to the 10 mil level. So just be aware that these things could be off a little bit. But wanted to give you at least one idea about how to go about doing this. So after I remove it, this is what we had here. I could select this here and go into File. And then from File, I could actually do an export of the DXF DWG file, which is what I did. Then what I did at this point is I brought in a PCB dock. And you're saying, why did you bring in a PCB dock? Well, first and foremost, because you can do a DXF DWG import both in the PCB and the library. But the reason I brought this in was that, number one, I wanted to make this a union, and number two, I had to deal with the resizing of things. And if I want to resize a bunch of things, I can't do it with components, but I can do it with primitives. So if I want to resize some stuff, just some quick tips for you guys. If you're doing DXF DWG, you bring this in, it's not the right size here, then what you can do is you can always go into Tools, you can do a Convert, and then you can create a union from the selected objects. And once you've got these as a union over here, if you select it again, it's a little cryptic how you do it, but nevertheless, if you right-click on any one of the representations that are in this union, you can say, hey, create union from selected objects, or probably not create, resize the union, okay? And now it's going to ask me to select a representation of the union again. Now it's got the entire union, and as long as I click and drag it, I can move this thing to where my heart's content. And actually, I had drawn, let me escape out of that. I had actually drawn this line because this line from this point where my cursor is located to this other point where my cursor is located was 11.8 millimeters, and I used that to do the rescaling. So I already did that over here. Now, what am I leading up to? Well, sometimes you have these really odd-shaped pads, or you need an odd-shaped pad. So what can you do with something like this? Well, there's two things you can do. My recommendation actually is that you take what you've already done over here and copy this into the assembly layer and then draw your pads on top of each other, and they can sit on top of each other, as we saw with this example over here, right? So in this example, we have pads sitting on top of each other. They're all pin 9. Okay, we can do the same thing over here as well. So if we go back over to our, if we go back over to this, all right, then we can add these pads in and make, as long as they're the same name, they'll all work just fine. Now, what if we have something that's a little bit more odd than that? Well, we can do that as well. Well, what we can do is we can actually do a polygon pour here. So let me delete this polygon pour and just walk through the motions of it. Okay, there we go. So to make a polygon pour of something, as long as it's enclosed, you simply select those lines that enclose it. You go back into Tools, you do a Convert, and then you use Create Polygon from Selected Object, the primitives. And there it is. Now, I got to double click into it and make it a solid. I don't know why it defaults to none, but nevertheless it does. The other thing I got to be, and I got to report it too. So I'm going to right click. I'm going to do Polygon Actions, and I'm going to report. I'll just report all since it's convenient. The other thing that's really important too is make sure I will have a pullback. So you will have to play with the rules a little bit in order to modify that. But nevertheless, what I can do at this point is I can sweep over this and do a copy of it. And if I bring it over to the PCB library, so let's go over here to my PCB library. I'll create a new part. Okay, so here's my new component, and I do a Control V. All right, and there is my outline. But more importantly, for those things that I had as polygon pours, they get converted. Polygon pours can't be polygon pours in the library because there's no rule definition for it. But they change them into copper regions. And I can also add my solder and paste masks to these things as well. In the past, you had to draw them separately. Now Altium handles them automatically, which is really nice. The only other thing you've got to do if you bring in something of this nature here is there's no designator, and we've got to have a designator. So what can we do? Well, the easiest thing for me to do, actually, I'm just going to go back here to grab one. I'll take this small one, okay, surface mount here. I'm going to do a right click and place it. Okay, so let's assume that this is, I'll hit the tab key. Let's assume that this is pin 20. Okay, so I got pin 20 over here, and I just got to embed it anywhere I need to. I'll just embed it in there, right click, and I'm done. And Altium will recognize the 20 here, and it will associate the pad to the pin. Lastly, what will happen is that when you go through the process, you link up the symbol, you put this into your schematic, and then you push it over the PCB. It will show as a short because the rest of this will be a no net, but pin 20 will actually have its net. So there's a really nice feature Altium has, just to make note of it. You'll go into Design, all right, and you will go into Net List, and you will say Update Free Primitives from Component Pads, and then Altium will associate the pad to the rest of the copper region, and you can do it as such. So just a few ideas for you if you really need to get into something insanely complicated as this. I just think it is a pretty extreme example, but at least it shows you some guidance on how to do this. And as usual, I'm at my hour over here, and won't have time for some questions, but feel free to write them up at this point in time, and I'll be more than happy to review those. We'll get a Q&A together, and if we need to do any subsequent videos, we'll certainly notify you as such. So again, thank you very much for your time, and we look forward to seeing you at our next webinar.